All right, let's practice. We are going to identify our valid and invalid forms of argument. And then we are going to, using only our valid forms of argument, because we can't use our invalid forms of argument to complete proofs, to complete the steps in a derivation. So, what you want to make sure that you can do, and this is an extension of the work that we did in Chapter 7, is distinguish between a valid argument form and an invalid argument form, either by the form itself or by way of a truth table. But then you want to get really comfortable, and this is much more specific to our work in Chapter 8, with employing the valid argument forms as rules in steps of a proof. So let's get started. First, the following argument is valid or invalid. You go ahead and do one of two things. Consult your rule forms from the text or your notes, or generate a truth table, and then come back and see what the answer is. This is a modus ponens argument, or an affirming the antecedent argument. Remember, if you want to, you can construct a truth table where you have your premise 1, premise 2, and conclusion laid out. You know there are 4 rows or lines for the horseshoe. The second line is false on a 4-row truth table. There is no determination to make for simple statement A and simple statement B. And we see that although there are 2 instances, rows 2 and 4, where the conclusion is false, in each there is a false premise. So there's no row on which the premises are true while, oh boy, the conclusion is false. Oh boy, I should not be writing this. It started off so well. All right, while the conclusion is false. I got like block writing. All right, next. This argument is invalid. Notice the difference between the last argument and this one. Here we are affirming the antecedent, or affirming the consequent, and that is a big fat no-no. So think about it this way. If I have 10 pennies, I have 10 cents. I have 10 cents, therefore I must have 10 pennies? No. You could have different permutations. So this is an invalid argument. We've already constructed a truth table for it earlier, but I wanted to do one for the modus ponens just to remind you. So here's the valid form, right? Notice the difference, affirming the antecedent versus affirming the consequent. How about this one? This looks like, at least a little bit, disjunctive syllogism, but it's not. This is an invalid argument form, and let's prove it. Are you guys comfortable with what I've done here, right? We have 2 simple statements, and so 4 lines of the truth table. The first statement is alternating true, false, true, false, or true, true, false, false. And then the second one is true, false, true, false. So we know that the disjunction is false when and only when each disjunct is false. And then all we're doing is taking the original values of A, because there's no operator working on this statement, and we simply plug them in. And then we're going to take B's values, which are true, false, and reject them by way of the definition of the tilde. Now, look at row number 1. False conclusion, true premises. This argument is invalid. All right, how about this guy? This should look familiar to you as one of the second set of valid argument forms known as Constructive Dilemma. Now, take a look at how many simple statements we have, right? We have 4. And recall also, if we want to construct a truth table to demonstrate this argument's validity, that we need to determine the number of lines by way of 2 to the number of simple statements. So here it would be 2 to the power of 4. So 2 times 2 is 4, times 2 is 8, times 2 is 16. So 16 rows, which would mean 8 true, 8 false for A. Then 4 true, 4 false for B. So this would be A, B, C would be 2 true, 2 false, all the way for 16, right? And then D, as the last, alternates, true, false, all the way down for 16 rows. Okay? Another way we could test this argument for validity is by an indirect truth table. Now, I'd like to try that with you just to see what you guys think about this. And it may be the case that you go, ooh, cool, it's so much easier than 16 rows. And some folks are going to say, oh my gosh, I don't like this at all. But let's give it a try. So here's how it works. We are going to first erase everything that I've written, and we are going to take each of these premises and lay them out just as we would if we were constructing a complete truth table. So we're going to take A horseshoe B dot C horseshoe D, A wedge C, therefore B wedge D. But instead of writing a complete truth table, we are going to construct what's known as an indirect truth table. And this is a really handy way when you're dealing with rows and rows and rows of truth table lines, of truth table calculations to determine whether or not an argument is valid without having to construct all those rows. So I also wanted to show you this method because I think it really hammers away at the meaning of validity. We know that it is impossible for an argument to have true premises, right? So a whole bunch of true premises and a false conclusion and be valid, right? This is an invalid argument, right? So what if we don't know that the argument is valid, or we know the argument's valid, but we want to show that it's valid? One of the great approaches is to assume the argument is invalid and then work backward. So what does it look like for this argument to be assumed invalid? True premises and a false conclusion. Then by working backward, what I mean is something we did in our practice for chapter 7, we take our truth definitions and we infer from the meaning of the whole, from the definition of the whole, what the parts will be or must be. So we've got, for a disjunction of a wedge, only one circumstance in which our wedge is false, and that's when both or each of our disjuncts is false. Okay, so remember what we're doing is we're testing this argument to see if we can maintain invalidity. In other words, if there is a row on which this argument comes up invalid, by the indirect truth table method, we'll find it. All right, so now if B is false, we're going to plug that value in to its respective locations. Now we come back out and we ask ourselves what we'd need to have in order to maintain a true conjunction. For this conjunction to be true, we need to have each of the horseshoes be true. But if we know that this consequence is false, what must A be in order for the horseshoe to come out true? Well, it's got to be false so that we end up with a true horseshoe. And then for the consequent D, we see as false, we'll need for the horseshoe to be true to have a false antecedent. Okay, fair enough. So far we've gone ahead and worked backwards, and we've maintained one premise as true, and we've got our conclusion as false, but we still have to plug in the values that were determined when working backward on each of these horseshoes. So A is said to be false, and C is said to be false, and that contradicts each of these, rephrase, this collective set of values contradicts the meaning of the disjunction, the definition of the disjunction, which means that we can't say that the wedge is true when each of the disjuncts is false. So when you run into a contradiction, you've just shown that it's impossible for the conclusion to be false if the premises are true. Now, you could have worked backward a little differently, but I chose to work backward the way that I did because since I knew what B and D had to be, I just started plugging in those values under their respective atomic or simple sentences. All right, let's take the same approach to the next argument, which looks really similar. So the last argument is valid. That's constructive dilemma, right? So just to go back, this argument for which we just constructed an indirect truth table is valid. This is constructive dilemma. Now let's test out this argument, and you'll see that it's very similar in form, but not identical in form to the last argument. What are we going to do? We're going to assume the premises are true and the conclusion is false. If this wedge is false, A must be false and C must be false. Let's take those values and plug them in. Now, in order for dot to be true, horseshoe has to be true. and we are saying that A and C are false, that means that B and D could be true or false, right? Because horseshoe is true in three ways. When the antecedent's true and the consequent is true, when the antecedent is false and the consequent is true, when the antecedent is false and the consequent is false. So it really doesn't matter what we make B, and it really doesn't matter what we make D, we're going to end up with a true horseshoe. Now remember, what I'm asking us to do here is to see if we can maintain invalidity. Well, we can, because we can go ahead and make B true and D true, plug those values in to B and D in the sentence B disjunction D or B wedge D, and we see that we have no contradiction. So there's no contradiction of the truth definitions. We've maintained invalidity. This argument is invalid. All right, what do you think this one looks like? Remember, we talked about imposters. This is an argument that looks like Modus Tollens, but it's not, and that's because what's happening is we're denying the antecedent, and that is an invalid move. It's invalid to infer a denial of the consequent from a denial of the antecedent. How do we know? For sure, let's construct an indirect truth table. Isn't it fun? Assume assume the argument is invalid. Okay, so if the conclusion is false, that means that B must be true, correct? So I'll plug that value in here. And if B is true, it doesn't matter what A is. The horseshoe is true, right? There's only one way in which horseshoe is false, and that's when the antecedent is true and the consequent is false. But let's finish this out anyway. So not A, tilde A is true, which means A is false. We plug that value in here, and we've not generated any contradiction, any truth definitional contradictions. The argument is invalid. Contrast that with, let's do red. Contrast that with Modus Tollens, aka denying the consequent. When we try to make this argument invalid, we're going to run into trouble. So we only know that the horseshoe is going to be true if B is true, right? So let's make B true. But notice, if we try to make B true, we run into a contradiction. We could also generate the contradiction another way. So if tilde A is false, A is true. If tilde B is true, that means B is false. Then when we plug that value in, we run into a contradiction. Horseshoe can't be true when the antecedent is true and the consequent is false. This argument is valid. This is Modus Tollens, or denying the consequent. Last one, I think, if I'm not mistaken, before we move on to proofs. Let's do the same thing here. let's assume the argument is invalid. We're basically saying to this argument, I don't believe that you're valid. So if we're assuming the conclusion, which is a simple statement, is false, we're going to plug that value in. The only way for A wedge B to be true if B is false is if A is true, but we can't have that. If not A is true, A's got to be false. So we run into a contradiction of our truth definitions. This is disjunctive syllogism. It's a valid argument. So when you run into a contradiction with your truth definitions, your argument is valid. All right, now let's take our rules and employ them in completing these arguments. So we're given the following argument: A or B, not A, therefore B or not C and D. So the line 4 is the conclusion, and we need to do two things here. We need to cite and justify how the intermediate conclusion and the conclusion of the argument is derived. So what you'll typically do, since your arguments, with the exception of simplification and addition, are two-line premise argument forms, is look at what you're given and then see if you can find a rule that maps on to the argument. So you'll notice that disjunctive syllogism has the same form as what you see in lines 1 and 2. So lines 1 and 2 by disjunctive syllogism give you line 3. And then you'll always use every premise that's given or derived, given 1 and 2, derived 3, until you reach the conclusion. So 4 has the main operator of wedge, and one of the ways that you generate a wedge statement is when you look at your rules by taking a statement, in this case B, and adding another statement to it. And that statement can be complicated, right? It doesn't have to be a simple statement. Okay, in this proof, we've got 3 premises and then 2 derived lines, the last of which is the conclusion. So one of the things that you should do is look at what you're given and see what rules might map. So for example, if you look at, let's say, lines 1 and 2, you'll notice that line 2 has nothing to do with the elements in line 1. So there's no way you can combine these two. But if you then look at lines 1 and 3 and you pull them off to the side, you'll see a Modus Tollens move. So as you're practicing with this stuff, one of the ways that you can go forward is to ask yourself the following. Okay, can I do anything with lines 1 and 2? Can I do anything with lines 2 and 3? How about 1 and 3? And then look, of course, at what you're, if you're given a constructed proof that you're completing, look at what's been derived, and then you can determine the best way forward. So this is the Modus Tollens move from lines 1 and 3. Now remember, I mentioned that every premise that you've either been given or derived as a sub-conclusion is going to be used. You won't have anything left unused. So that means that you need to use C. In addition, you've derived A but haven't yet used it. So since there's one more step, you'll need to use A. And you can tell that dot is the main connective here, main operator, I should say. And so lines 2 and 4 have been conjoined to yield the conclusion. Okay, now once again we have some complicated statements, right? We've got one statement that's got two operators, one statement that's got two operators plus a pair of parentheses. But remember what you're doing. You're focusing on the main connectives. So for example, when you see that you have a dot, one of the first things you might consider doing is eliminating the left side, right? Simplifying. And notice that line 4 is perfect for the move that I just talked about. Line 1 simplified gives you line 4. Then take a look at line 5. Line 5 is C horseshoe D. Notice that C horseshoe D happens to be the right side of a wedge, and I've just inferred that the left side of wedge is not the case. So from lines 3 and 4 by disjunctive syllogism, and keep looking back and forth from the proof to your rules, proof, rules, and you'll start to see them more clearly as you go forward. We get by disjunctive syllogism C horseshoe D. Consider also checking off premises as you have used them. Doing so will let you know that you have used them. You may use them again, but it also tells you what you haven't yet used. So take a look at 2 and 5. And by Modus Ponens, you've got 6. So now you've used all 5 of your given and derived lines. And that means then that line 7, since you know that's the termination of the proof, has to come from line 6. You've got a disjunction. There's only one rule that takes you from a statement to that statement disjoined with another, and that is addition. Okay, now what I'm going to do is ask you to go ahead and pause the video, see if you can complete this proof on your own, and then come back to see what I've done. All right, I know there are a lot of arrows here, but I think you'll be able to follow them. First, let's look at line 4. Line 4 comes from, let me change pen color here real quick. Line 4 comes from line 3 by way of addition. 5 comes from 1 and 4 by constructive dilemma. And again, cross-check these moves against your rule forms, against the forms that you have highlighted in your text or in your notes, where you've got, for example, P horseshoe Q dot R horseshoe S, P or R, therefore Q or S, right? Like the disjunctive syllogism move we just made. Then line 6 comes from 2 and 5 by disjunctive syllogism. And then lastly, we're going to use C again, conjoining it with F. All right, so I hope this practice has been helpful. As always, if you have questions, problems, confusions, don't wait, let me know so that we can work through them. But you now have everything that you need to complete this course successfully. So I hope you've had lots of fun, as much fun as I've had, and I hope that you will certainly think about taking another philosophy course if you haven't done so already. This work that we've done gives you some really good analytical tools that you can take with you anywhere, but certainly into more work in philosophy.